Hello friends, thanks for watching Edupedia word videos, virtual word free education. Today in this video we'll be learning about polynomials. The contents of this video are meaning, degree, zeros and graphical representation of polynomials. So let us start with the meaning of polynomial. Polynomial word consists of two terms, poly and nomial. Poly means many and nomial means terms. Therefore, an expression of algebraic terms. The word algebraic means the terms contain variables, example x, y, etc. especially the sum of several terms that contain different powers of the same variable or variables. So, in general, sum of different powers of the same variables is known as polynomial. Let us clarify this with some example. Sum of different powers of same variable. Before starting the clarification, let us know the lower powers. X raised to power 0 equals nothing but 1 because anything, that is any number raised to power 0 gives us 1. Similarly, x raised to power 1 equals x because any number raised to power 1 is the number itself. Now, x raised to power 1 by 2 is nothing but under root of x. Similarly, x raised to power 1 by 3 is cube root of x. Now, in general situations, we sometimes encounter an expression where the numerator is 1 and we have a power term in denominator. To bring such a term in numerator, just negate the power sign. That is, if we are given with 1 over x cube, we can write it as x raised to power minus 3. Similarly, 1 over x square equals x raised to power minus 2. 1 over x equals x raised to power minus 1. Now let us have some more examples. See, x cube plus x square plus x plus 1. Here we have a variable, that is x, and different powers of this variable. Therefore, it is clearly a polynomial. Let us have another example of x square minus x plus 1. Clearly, it can be rewritten as x square plus minus of x plus 1. Therefore, here again a variable, the sum of different powers of the variable. Therefore, it is also a polynomial. Now, let us have another example, 3. Now, here it doesn't contain any variable, but it can be modified into a variable. That is, 3 is nothing but 3 into 1. Now, 1 from here is x raised to power 0. Therefore, we are having a variable over here also. Therefore, 3 is also a polynomial. Similarly, 1, 2, 1.5, etc. all are polynomials. Now, polynomial in one variable. Polynomial in one variable can be represented as p of x equals an x raised to power n plus a of n minus 1 x raised to power n minus 1 plus up to so on. Here n is a natural number. Natural numbers are numbers like 1, 2, 3, etc. Now the terms an minus 1, a1, etc. are known as coefficient of respective powers. These coefficients must be real numbers. By real numbers we mean the numbers encountered in our daily life like 1, 1.5, 2.5, minus 1, 2, etc. That is 1 plus minus 2 plus minus 3, 0.5, even pi. All the numbers are real numbers. Even 0 is also a real number. Now the polynomial px can also be represented as y equals px. Now here is a caution for all you guys. All the given terms are not polynomials. Let us see how. The first term says 1 over x minus 1. See, we have given two conditions, that is n, in our definition of polynomial in one variable. Must be a natural number, and an coefficients must be real numbers. Now if we bring this denominator into numerator, then we have to negate the power of this whole term, which is nothing but 1. Therefore we have a negative power which when decomposed will prevail in the consecutive terms. Therefore a multiple of this negative term will be prevailing in these terms, and hence it can never, the power can never be a natural number, and this power must be natural number for px to be a polynomial. Therefore it can never be called as polynomial. Similarly, another example, under root of x plus 2. Here under root x is nothing but x raised to power 1 by 2 plus 2. Now this power is again not a natural number, that is, it is not in the form 1, 2, 3, etc. Therefore it is also not a polynomial. Let us have another example, 1 over x square plus 2x plus 3. Now again, like the similar case, x square plus 2x plus 3 raised to power minus 1, this negative power will prevail in all the terms and will give a negative power. Thus n will not be a natural number here. Therefore it can never be a polynomial. Now what is the degree of polynomial in one variable? The degree is the highest power of x in p of x if px is a polynomial. Now if px is a polynomial, then powers must be natural numbers, which have been stated in the previous slide. Let us find out degree of some simple terms. let us have an example: x cube plus x square plus x plus 1. The degree in the slides is said as highest power of x in P of x. Now if x cube plus x square plus x plus 1 is a polynomial, then the highest power clearly is 3. Therefore degree equals 3. Let us have another example: P of x equal to x square minus x plus 1. Here again the highest power is 2. Therefore degree equals 2. Now let us have one more example: 3. We have proven that this constant term is also a polynomial. Now converting it into variable form, we get 3 into x raised to power 0. Clearly the highest power is nothing but 0. Therefore degree here is 0. Now let us have a polynomial in two variables, that is x and y. 3 x cube y square plus 4 x square y plus x y plus 9. Now in such a case, the power of this term is the sum of power of these two terms. That is, here power is 3 plus 2 equals 5. Here the power is 2 plus 1 from y, which is 3. Here the power is 1 plus 1 equals 2, and here the power of x is 0. Clearly the highest power is 5. Therefore degree equals 5. Now let us know some terms related to lower degree polynomials. If degree of a polynomial is 0, then the polynomial is known as a constant polynomial, whereas with degree 1, the polynomial is a linear polynomial. With degree 2, it is a quadratic polynomial. With degree 3, it is a cubic polynomial, whereas a polynomial of degree 4 is known as quartic polynomial. Now, what are the zeros of a polynomial? A real number k is said to be 0 of a polynomial px if p of k equals 0. That is, if in a polynomial px we put the value of x equal to k, we get output as 0. Zeros are also called roots of a polynomial. To find 0, put p of x, the given polynomial, equal to 0 and find the value of x. Let us simplify this slide. Firstly, it was stated that if k is a 0 of px, then p of k equals 0. The second statement was to find 0, put p of x equal to 0 and find values of x. Now let us find out zeros of some polynomials. The first polynomial is a simple one, px equals x plus 1. To find 0, put p of x equal to x plus 1 equal to 0. That is, px equal to 0 implies that x plus 1 equals 0, which implies x equal to minus 1. Therefore x equal to minus 1 is the 0 of polynomial. Now second polynomial, px equal to 2x plus 3. To find the 0, again put px equal to 0, implies that 2x plus 3 equal to 0, which implies 2x equal to minus 3, which implies x equal to minus 3 by 2. Therefore, this is again the 0 of the given polynomial. Let us have one more example. X square plus 5x plus 6 equal to 0, equal to px. Now the given equation is a quadratic equation. To find the 0 of such an equation, we will be studying in further chapters a factorization method to deal with such equation, which will fetch us x plus 3, x plus 2 equal to 0, which will be giving us x equal to minus 3 and x equal to minus 2 as the two values of x, which are here zeros of x. Now the last example, x square plus 1 equal to 0. If we have to find this zeros, bring the 1 to RHS, which gives us x square equal to minus 1. Friends, we can easily see that 1 square equals 1, even minus 1 squares equal 1, 2 when squared equal 4, minus 2 when squared equals 4. That is, even the square of a negative term is a positive term. Therefore, square of a term can never output to a negative term. But here, square of a term is giving us a negative term. Therefore, it is a contradictory statement and it can never be possible. Thus, in such a case, we have no zeros at all. Thus, we can easily see that here we have 1 0, here we have again 1 0, again here we have 2 zeros, that is minus 3 and 2, the number is 2. Here we have no 0, that is n equals 0. Thus, if we find the degree of all the polynomials, we will see here the degree, that is the highest power, is 1. Here degree is again 1. Here degree is 2. Here degree is 2. Now degree and the number of zeros are same. Here again degree and number of zeros are same. Here also degree and number of zeros are same, but here degree is 2 whereas number of 0 is 0. Thus we can easily see that either the number of zeros n are equal to degree or number of 0 n less than degree. Thus n less than or equal to degree. Thus the maximum possible number of zeros are the degree of the polynomial. That is, maximum possible zeros is nothing but the degree of the polynomial. Now guys, let us have graphical representation of some simpler polynomials. Before having the graphical representation, let us know how to plot a point. If a 2, 3 is a point, then 2 is x coordinate, whereas 3 is y coordinate. Polynomial px equal to x plus 10 can also be represented as y equal to px, that is, we can interchange px with y. Let us clarify this slide. If a2, 3 is a polynomial, then 2 is x coordinate and 3 is y coordinate. See, this is our Cartesian plane. These are the points. Here 2 means the location of 2 on x-axis, which is this. This axis is known as x-axis, whereas this axis is y-axis. Now locate 2 on this axis and make a perpendicular from this axis. Similarly, for 3, locate 3 on y-axis and make perpendicular on y-axis. The point of intersection is the required point. Now let us plot the graph of y equals 2x plus 3. For plotting a graph, we will tabulate different values of y for different values of x. But before plotting the graph, let us find the 0 of this graph. Guys, to find 0 of this polynomial, let us put px equal to 0, which gives us 2x plus 3 equal to 0, which gives x equal to minus 3 by 2 as the 0 of this polynomial. Now, to tabulate this graph, let us find different values of y for different values of x. At x equal to 0, y equals 2 into 0 plus 3, which gives us 3. Therefore, at x equals 1, y equals 2 into 1 plus 3, which gives us 5. At x equals minus 1.5, y equals 2 into minus 1.5 plus 3, which is equal to minus 3 plus 3 equal to 0. Now let us plot these points on the Cartesian plane. At x equal to 0, we have y equal to 3, this point x0 and y3. At x equal to 1, we have y equal to 5. At x equal to minus 1.5, that is midway between minus 1 and minus 2, y is 0, so it lies on x-axis. After joining these points, we get the graph of the given polynomial. Clearly, if we have a closer look at this point, it gives us minus 1.5, 0, which is nothing but minus 3 by 2, 0. Now, this is nothing but the 0 of the given polynomial. Therefore, 0 of a polynomial has the y coordinate as 0 along with it. In this case, let us have a clear look at the graph. See, at x equal to minus 3 by 2, y equals 0. Let us have one more example, and then we will be generalizing the solution. Now see, y equals x square minus 3x minus 4. To find the zeros of such a polynomial, put x square minus 3x minus 4 equal to 0. Again, it is a quadratic equation and its factorization method will be studied in a later chapter. The factorization of such an equation will give us x minus 4 and x plus 1 as two factors, which will give us x equal to 4 and x equal to minus 1 as the two zeros. Now, if we look at the graph plotted in the Cartesian plane, we see such a shape. Now see, again the zeros, that is minus 1 and 4, which have been shown in the solution, are plotted here. Again, at these zeros the coordinate of y are 0, and at these 2 points the graph is cutting y-axis. Therefore, we can say that zeros of the polynomial y equal to px are the x coordinates of the point where the corresponding graph crosses the x-axis. Now, let us know how we can find the number of zeros from the graph. See, the two graphs we studied were 1 and 2. This was the zero of the first graph, and these two were the zeros of the second graph. Clearly, by seeing the graph, we can say that it has 1 0 because it cuts the graph at one point. Now, in this case, this curve cuts the x-axis at 2 points. Therefore, we have 2 zeros in this curve. So, let us have some more example to find out the numbers of zeros. Now, in the first graph, the graph cuts the x-axis at 2 points. Therefore, number of zeros here are 2. In the second graph, the graph is cutting x-axis at 3 points. Therefore, number of zeros equal to 3. Now, in the third and the fourth graph, the graphs never cut the x-axis. Therefore, number of zeros in both the cases is equal to 0. In the fifth graph, the graph cuts the x-axis at a single point. Therefore, number of zeros equal to 1. In this graph, the graph cuts x-axis at 2 points. Therefore, number of zeros equal to 2. Now, this is a very interesting case. Here, the graph is never cutting the x-axis, but instead, it is touching the x-axis at a single point. Therefore, number of zeros equal to 1. Here again the graph cuts the x-axis at a single point. Therefore, number of zeros equal to 1. Now, in the last case, the graph cuts the x-axis at a single point and touches the x-axis at one point only. Therefore, number of zeros equal to 1 plus 1, that is 2. So, here's a generalization. If the graph does not crosses the x-axis at all, there is no zero. There is one zero if the graph crosses the x-axis one time. If the graph crosses the x-axis two times, there will be two zeros for the given polynomial. So that's all for today, friends. In the next video, we'll be watching relationship between zeros and coefficient of a polynomial. Thanks for watching Edupedia videos.